Hello everyone, welcome back to my messy basement. Welcome back to Comp 3430 operating systems. We're down another week, and so I want to take the time to kind of give you a quick summary of where we're at, what we've been doing this last week, and how the learning outcomes are fitting into what you're being assessed on, and where you can find information about those learning outcomes. So let's take a look at the course schedule and the ROAS. Here's the topics that we have for week 2. At the beginning of the week, we kind of focused more on learning outcomes from week 1, and specifically related to things like pipes and IPC. And we looked a lot at how the process control block and the open file table are modified when we do things like pipe and when we do things like dupe2, and how that kind of facilitates communication between processes. So that was related to this learning outcome here. Determine what an operating system might need to know about a process, and describe how an operating system manages processes. So data structures, control of processor and modes. That was not so much in what we were talking about, but data structures definitely was. This is also related to communication. So now we're looking at describe how the operating system supports and implements shared memory, signals, pipes, and FIFOs. And we've kind of been implicitly doing this as we get into the later part of what we were doing this week with threads and locks. Compare and contrast the shared memory and message passing programming models and the relationship as seen through the lens of synchronization. So everything that we're doing with locks in pthreads is a synchronization mechanism for shared memory. Threads are kind of like what we're thinking about when we're talking about shared memory. At the beginning of this week, though, we spent most of our time talking about FIFOs, pipes, and how those things modify the process control block and the open file table. When I'm thinking about describing how the operating system supports those things, and when I'm thinking about describing how an operating system manages processes, these are the kinds of things I'm thinking about. So process control block, how do these system calls change the process control block? How do these system calls change the open file table? What kinds of things does the operating system have behind the scenes to enable things and facilitate things like communication between processes? With the learning outcomes for threads this week, we've got compare and contrast processes, threads, and applications. This is coming from a combination of chapters 4 and 5, 26 and 27. So 4 and 5 were more about processes, 26 and 27 were about threads and concurrency, finer grained concurrency. This is something that you haven't been assessed on in terms of lab or in terms of an assignment, and this is something that you should probably expect to see on something like a test. So this is something that's more like a written answer. The next learning outcome here, write code that uses library calls to create and manage threads. You are going to be assessed on this in Lab 2 and in Assignment 2. And this is where we're doing things like using pthread create and pthread join to create threads and then wait for them to finish. This is described in Chapter 27, the Thread API, but we also did this a lot in class. Describe the operating system data structures needed to manage a process and those needed to manage a thread. This comes from Chapter 4, so this is related to last week when we're thinking about things like the process control block and the open file table. This also comes from Chapter 26. And the takeaway from this is that we've got this idea of a process control block, and part of that idea at the beginning of a process control block was that it has things like the state of the CPU as you're pulling things off of the processor. So when the operating system needs to regain control of the processor, it needs to work with the hardware to get some of the data off the registers of the processor, save that state, save that context, and then it will do the rest on its own. So it will take the rest of the context off. The process control block has a context, so the values that the registers had when they were pulled off of the processor. That context is actually what is the thread control block, and this is described in chapter 26. The thread control block, there can be one or more thread control blocks in a process control block. So every process needs to support one or more threads of execution. So we'll have one or more threads. Each of these threads has their own independent stack. So it's not just the context, but it's everybody's got their own stack. And then the kind of related to this compare and contrast processes and threads, the relationship between processes and threads in terms of shared virtual address space. So the process control block has this idea of that shared virtual address space, and then the thread control block has the context for a thread of execution plus things like the stack. The next learning outcome here, this one described data structures. You're not being assessed on this in an assignment. This is one that you could expect to see on something like a test. The next one, identify the critical sections requiring mutually exclusive access in a piece of code that will be run concurrently using threads or processes. This is described in chapter 27, and this was an activity that we spent quite a lot of time in class doing, taking a look at some code examples and trying to find out whether or not there were critical sections in that code. You're going to be implicitly doing this when you're writing code that uses threads. You're going to be doing this when you're writing code that uses threads, but this is also something that could be on a test. You know, the activity that we did in class was, hey, look, here is some code. Let's try to find out if there is a critical section here, and what is the critical section? What are the circumstances that lead to that critical section happening? You're going to be implicitly assessed on this when you're doing assignment 2 and when you're doing lab 2, but you may also be assessed on this in a test. Write code that uses pthread mutex lock to protect a critical section. We did this in class for one example. We did this in class for that textbook example of the counter. You're going to be assessed on this in the assignment 2 when you're building up a multi-threaded application. And I'm not expecting you to use pthread mutex lock as an actual call on a piece of code in a test. This is going to be something that's mostly just in assignments. Identify correct and incorrect implementations that attempt to protect a critical section. Similar to identify critical sections, you're going to be implicitly assessed on this in assignments, because you're going to write code and maybe it's not going to work correctly. But this is something that you are going to implicitly be doing there because you're going to identify that as maybe an incorrect implementation of an attempt to protect a critical section. You're also going to be assessed on this in lab 2, where you're going to be building your own locks, and you're going to be kind of building them iteratively, where you're going to start with a broken lock and then work your way up to something that actually uses atomic operations to build and implement a correct lock. This is in chapters 26 and 27. And then this is also going into part 2 of this week with locking and deadlock. And we'll look at that again in just a second. But this is coming from chapters 26 and 27 as well. We started looking at deadlock at the very end of class yesterday, and we'll continue taking a look at deadlock on Tuesday next week. The learning outcomes here are primarily coming from the textbook chapters, and we'll spend a little bit more time on deadlock in class. Identify correct and implement incorrect implementations that attempt to protect a critical section. These related to week 2 and week 5. That's a typo on my part, I'm sorry. That's kind of a fallback to previous offerings of this course. This is now also chapters 28 and 32. So it's chapters 26, 27, 30, 28, and 32. In chapter 28, they're talking about like how do you actually implement locks and which ones of these are not actually going to work despite looking like they're going to work. Chapter 32 is common concurrency bugs, and this is like, the placement of locks and the acquisition order of locks. What is an incorrect implementation of that? So this learning outcome is going to be assessed twofold in terms of, is this a correct implementation of a lock data structure? And is this the correct place to put locks to try and protect a critical section? That's something, again, that you could be assessed on in a test. You're going to be implicitly assessed on that in um, your assignment. You're going to be explicitly assessed on that in the lab because you're going to be implementing incorrect implementations of locks. Use atomic hardware instructions to implement a lock, and this is from chapter 28. I'm not going to talk about atomic instructions in class. I'm not going to talk about what's in chapter 28 in class very much, if at all. This is going to be assessed in lab 2. Again, this is where you're actually going to go through the process of building a lock implementation. Identify code protecting a critical section that would result in deadlock and propose solutions that would avoid and or prevent said deadlock. So this is coming from chapter 32 of the textbook, the Common Concurrency Bugs chapter. We're going to finish this on Tuesday next week. So we started looking at that code sample in class, the transfer between accounts, multi-threaded transfer between accounts code sample. This is an identify code protecting a critical section that would result in deadlock. You may be implicitly assessed on this in your assignment. Like you may have code that you write yourself that winds up deadlocking. It's possible for that to happen. But it's more likely that you're going to see this on a test or a final exam. Here's some code. Is it possible for this code to deadlock? And what would you change about this code to guarantee that it does not deadlock? And this is related to that 4 conditions that must hold for deadlock. Write code that uses pthread locks and condition variables to implement a semaphore. As I'm reading this, and looking at what I've written here, chapter 31 is optional, and chapter 31 is the chapter about semaphores. I'm actually going to make a change to our learning outcomes here, and I'm just going to strike this one. So use pthread locks and condition variables to implement a semaphore. We're just not going to, you will not be assessed on that. That's not something I'm asking you to do. If you want to take the time to read about semaphores, please be my guest, go right ahead, but we're not going to talk about that in this course in this term. So after class today, I'm going to update this document, and I'm just going to strike this out. So it will still be there, but it's going to be stricken, so you don't have to worry about it in terms of assessments and stuff. Use condition variables in a program. Use condition variables in a program is in chapter 30. They describe both the mechanical use of the API for condition variables, but also kind of like what condition variables are and how they work. Really briefly, condition variable it's kind of like a lock, where a lock says you are allowed to have exactly one thing entering this critical section. A condition variable is you could potentially have many, but a condition variable and a lock also have different semantics attached to them. So condition variables are very explicitly a queue data structure. There's that queue again. It's a queue data structure, where a lock is not explicitly a queue. It may be implemented as a queue underneath, but it's not explicitly saying that you're going to be queued up after this. So we may take a look at this next week very briefly in class, but this is going to be something that you will be using in assignment 2. You may be using this in assignment 2. And with that, we may look at it the week after next, as opposed to next week. We'll kind of like leap back and take a look at threads with condition variables here in the context of taking a look at assignment 2 after the term test is over. Looking forward, in week 3, we've got the term test. We've got that scheduled on Thursday. Lab 2 is scheduled this week. It's due after the term test on Thursday. The class that's rescheduled on Friday is canceled. I don't know. I don't want to have a class on Friday after we write a term test. I think everybody just needs the break after that, so it's reasonable to cancel that class. Lab 2 is what I would consider to be a little bit more straightforward than what you did for Lab 1. Take a look at it early to get a sense of what you're doing. The first introduction to the use of condition variables is in Lab 2, so it's an opportunity for you to practice it a little bit before we get to assignment 2. But I'm not going to talk about condition variables in class this week, just in terms of I want to get to scheduling before we do that. All right, so that's it for the roundup this week. Again, I hope this is helpful, and I otherwise hope that you have a really great long weekend, and I will see you on Tuesday next week. Bye.